This is ECE 343, Signals and Systems. This will be the first part of Chapter 4. Up to this point in the semester, we've been dealing with signals and systems completely from the time domain. We've looked at signals and systems using the independent variable time, either t or n, and doing all of our analysis, all of our computations in that domain. What I believe many people will find is that some of the operations that we need to do in the time domain are hard. So solving a differential equation is difficult in the time domain. Solving a difference equation is difficult in the time domain. Doing operations like convolution are difficult in the time domain. This chapter, chapter 4, is going to make a transition, and it's a transition that will remain for the rest of the semester. We're going to leave the time domain and we're going to go to what is called the transform domain. The transform domain replaces the time variable with a new variable, the transform variable. We usually think of that transform variable as a form of frequency. So this frequency domain or transform domain, we'll find out, provides a lot of advantage over the time domain. It gives us all sorts of computational advantages. It gives us intuition advantages. Operations that were difficult before, like solving differential equations, become quite a bit easier. They become solving algebraic equations. Understanding things like system behavior becomes difficult. Looking at a difference equation or a differential equation and trying to say, what's the behavior of that, becomes something like looking at frequency response and saying, oh, it's a low pass filter, or oh, it's a high pass filter. So really, this transform domain is a necessary step for us to be able to efficiently and confidently deal with signals and systems. In order to help us get to a full understanding of Laplace transforms, almost everybody should have had, everybody should have had some introduction to Laplace transforms before in their circuits class. We're going to do it a little more in depth, a little more detailed, a little more complete. And to get us going on this, I'd like to consider a signal from a system standpoint. So let's go ahead and let's consider an input signal x of t, which is a complex exponential, so e to the st. Where, right, that variable s is some complex, potentially complex number, which I'm going to go ahead and write in rectangular form as sigma plus j omega. So we're going to consider a signal x of t, e to the st, so a pure complex exponential, right? Consider that signal, and we're going to input into a linear time invariant continuous system, right? With some impulse response h of t, right? What do we know? We know that the output of this system, this is something we studied back in chapter 2. We know that the output of that system, y of t, is going to be equal to x of t convolved with h of t, and putting that into the convolution integral, it's an integral minus infinity to infinity. I can choose what thing I want to flip and shift. I think I'm going to go ahead and flip and shift x. And so I'm going to leave h alone. So we'll have h of tau, and I'm going to have x of t minus tau, right? But x is just e. So I'm going to have e to the s, and I'm going to have t minus tau d tau. Something along those lines. This is something we've actually looked at before. I'm going to do a little simplification on that exponential. I have an exponential of a sum. I can break that into a product of two exponentials. One of them, e to the st, not being a function of the variable of integration, can be brought outside. So I'm going to get an e to the st, right? And then I'm going to have an integral minus infinity to infinity, h of tau, and then I have that other side of the exponential, e, right, to the minus s tau d tau, something along those lines. One of the things I can notice here is that that entire integral expression, let me go ahead and put a dotted box around that guy, that entire integral expression, right, has no value or no dependence on t. So we can see here there is no dependence, right, dependence, need to get this right, dependence on the time variable t, right? So that means that that term is a constant with respect to t. Now it does have some dependence on that input frequency variable s. And so we will go ahead and write this as a constant with respect to time, but a function of the frequency s. So let's let this whole thing, right, this whole piece here, that dotted box, that integral there, just be designated by capital H sub s, something along those lines. So what do we find? We find that y of t is equal to e to the st times a complex constant that depends on the frequency of the input, h of s, something along those lines. This is a beautiful result. I'm going to go ahead and draw it out just as our kind of block diagram representation of systems would allow. So I'm going to go ahead and put my LTIC system in there. So I have a linear time invariant continuous system. I know that there's my input x of t. In this case, I'm letting it be that exponential e to the st. And then I find that the output y of t is equal to the same exponential e to the st, just modified by a complex constant h of s, something along those lines. Turns out, and we've seen this before, we've done the same derivation before, that exponentials are a truly unique kind of input for linear time invariant continuous systems. You put a complex exponential in of some particular frequency s, you get exactly the same exponential out. It just gets modified by a complex constant. It maybe gets a gain change or it gets a phase change, but the shape of the waveform is undistorted, it's unchanged. Almost no signals have this property. In fact, there's none that I can think of that generally have this property when it comes to linear time invariant systems. If you put in any other kind of signal, except for the most trivial of systems, if you put in any kind of other signal into there, you're going to see that their shape changes. So you put a square wave into a low-pass filter, it's going to come out and it's not going to be a square wave. You put a triangle wave into a low-pass filter, it's no longer going to be a triangle wave. You put a voice pattern into a linear time invariant system, you're going to find out that that voice pattern gets some shape distortion. Now you put a sinusoids are just a special case of complex exponential. You put a sinusoid or a complex exponential into that system, you get exactly the same sinusoid or complex exponential out. The only thing that can change is its magnitude and phase, that complex constant that's getting multiplied. The other thing that I would just highlight here, right, is that this expression off on the left, right, this expression over here looks like multiplication. That looks, right, like multiplication rather than having our convolution. We did do a convolution to get it, but for this particular case, it comes out looking a lot like multiplication. So the general operation here, if we can break things down into sinusoids, right, the general thing here is that if you got things in a sinusoid or a complex exponential form, you probably aren't going to have to do all that convolution. You just multiply by the corresponding gain factor h of s. All of this leads to this idea that exponentials are unique to linear time invariant systems and that their propagation through those systems is very simple. And if we can decompose, if you will, a signal into just these exponentials, it should be tremendously helpful. Okay. So let's go ahead and summarize something about that complex scale factor. So the complex scale factor, right? So the complex scale factor h of s, right, is called a system function, is called the system function. It's also called the transfer function. We'll find out later. And this is unique by looking at an integral that involves the unit impulse response. It's also called the transfer function. Okay, and we know that it is given in the following way. H of s is equal to an integral minus infinity to infinity, right, of h of tau e to the minus s tau d tau. Now, because I'm integrating, right, with respect to a variable of integration, we call that tau here, that variable of integration disappears. And really, there's no reason that we have to be calling it tau. We could call it whatever we wanted. So I'm going to write this in just a slightly different way. I can just say alternately, but completely equivalently, alternately, right? We can write this as h of s is equal to an integral minus infinity to infinity little h of t e to the minus st dt. These are exactly the same expressions, okay? Variable of integration disappears, so it doesn't really matter what I call that variable of integration. I like this one better because it does see something here where if I look off on the left-hand side, right? If I look over there on the left-hand side, I see some t's over here, right? But I integrate, so there's the t's, right? I integrate those out, and what I find over here is just s's. So you can think of this as a conversion, right? It takes this time domain function, h of t, and it converts it to the frequency domain, or the transform domain, if you will. There's a time domain function off there on the right, and we undergo some sort of transformation, and we find, right, a different or an alternate kind of representation, this h of s. It's just purely a function of s. For those of you who have have a little memory of your circuits days, you'll also notice that this entire expression is something you've certainly seen before. This entire expression here is the Laplace transform. So this is the Laplace transform of that signal h of t, right, which we assign to some new variable that is a function of the transform variable s, right? So h of s, something along those lines. So when we look at a complex exponential going through a system, right, we see that that same complex exponential comes out as long as the system was linear time invariant, multiplied by a complex factor. And that complex factor is just the Laplace transform, something you've seen before. It's just the Laplace transform of that time domain signal, right, h of t, the unit impulse response of the system. Okay, so one of the sides of this, the Laplace transform tells us how to get from the time domain to the transform domain, but it doesn't necessarily tell us how to get back. More completely, we should be able to, in a transform domain, go in either direction. So I'm not going to prove this. The proofs aren't easy. These are difficult ones. I'm just going to give the Laplace transform pair, and then we're going to start working with it. So more completely, I should say, maybe. So more completely. We can go time to s or s to time with the Laplace and what is called the inverse Laplace transforms. So let me go ahead and write those out. The Laplace transform of a signal x, we'll call that x of s. And one thing you'll notice here is that I use a capital variable for the transform domain. So if I have a time domain signal, little x of t, I'm going to let its transform be cap x of the variable s. So that way we'll always have this nice explicit link between the time domain and the transform domain. What we're going to see change is whether it's a function of time or a function of that frequency variable. So we've already seen this one, the Laplace transform of the signal minus infinity to infinity of that signal x of t e to the minus st dt, something along those lines. The other side of this guy tells us how I can recover x of t. So I can get x of t from the transform domain. And so this is where things get a little weird. It's 1 over 2 pi j, and then I'm going to have an integral going from c minus j infinity, and c is a constant. We don't have to worry too much about it right now, to c plus j infinity of our transform variable x of s, right? And it's going to be e to the st ds, something along those lines. So the one on top, right, this guy here is the Laplace transform. And if I was going to be more complete, and I will here just for a second, this Laplace transform, this is actually called the bilateral. We'll get more to this distinction later. This is the bilateral Laplace transform. And then this one on the bottom is the inverse Laplace transform. Inverse Laplace transform, something like that. So if I transform a signal x of t to get x of s, I can go through this inverse Laplace transform and return and find my x of t. They're a unique transform pair. Going to the transform domain doesn't destroy the signal. It's a different perspective of that signal. It's getting a different view of it, but it is equivalent in the information that it contains, and we can always go back. There's a cost. You got some math to do, right? You have some math to do to get the Laplace transform, and you have some math to do to get back to the time domain. But the information contained in x of t and the information contained in x of s are equivalent. You can get one from the other. I'm going to say that this particular equation right here, this equation here, this inverse Laplace transform, this is difficult to evaluate. It's difficult to evaluate directly. And because of the prereqs in this particular class, we don't require a prerequisite of having taken complex variable theory in the mathematics department. It's usually a 400 level class or even a grad level class. We don't have that complex variable theory class in there. We really aren't equipped to carry this integration out directly. Why do I say that? If you take a look at it, I'm just going to say note, right? ds, right? That is a derivative with respect to a complex variable s, a complex variable s. So this isn't the normal kind of integration that you learn back in Calc 1, 2, or even Calc 3. All of those are differentiation or integration with respect to a real variable. This is differentiation with respect to a complex variable. You get some further notes of that, right? You get some further notes of that by looking at the limits of integration that are going on here, right? Those limits of integration end up being also with respect to complex numbers. So there's complex numbers in there as well. And I think for most of you who've gone through Calc 1, 2, or 3, you've never seen anything like this where you've got a complex number in the integration limit, something along those lines. So making it simple here, I'm just going to say that the vast majority of people in this class will not have the mathematical prerequisites to directly evaluate this particular equation. You didn't have it either when you worked with these equations back in circuits. It doesn't have to be too much of a limit because there's some other things that we can do in order to transform back to the time domain. That's part of the reason we spent a bunch of time talking about partial fraction expansions and looked at techniques like that. We're going to see that through partial fraction expansions and a series of properties, we can go ahead and do the inverse transforms in an indirect method, and that's the way we'll handle it. Why do I end up giving this equation since we can't evaluate it? Why do I give this equation that tells us how to do the inverse Laplace transform? I do it because of the story that it provides. And so I'm going to go ahead and make a copy of this guy one more time. And I would like to think a little bit about what the story is behind this equation for the inverse Laplace transform. So I'm going to go ahead and plug this guy back in here, and let's take a look at this guy in just a minute and think about the story. The story in this particular case, right, is something like this, right? We have a signal, and we are saying it's equivalent or it can be represented as, right? There's a scale out factor up front, so we'll deal with that as we go along. We can combine that with the x of s if we want. But we have an integral, so that's a sum. It's a limit of a sum, right? And then we have some scaled, if you will, right? Some scaled. And what are we summing and scaling together? Well, the time domain functions here are some complex exponentials. Complex exponentials. Right? Okay, so let's think about this. It says take an old signal that you want, and we are going to represent it as a sum of scaled complex exponentials. This isn't all that different than what we saw from like a Taylor series expansion. What did Taylor say? Taylor said you can take a signal and represent it as a sum of scaled polynomials. What did the sifting property say, for example? It said you can take a signal and you can represent it as a sum of scaled and shifted delta functions. So we've looked at these kind of decompositions where we've taken an arbitrary signal and we've represented it as some scaled sum of somethings, right? It's just now that our somethings are going to be these complex exponentials. Why do we want to do that for this class? Well, we want to do it for exactly the reasons that we saw up here. When you put a complex exponential in, right? When I put a complex exponential in to a system, it comes out in a really simple form. It comes out as the exact same complex exponential, just modified by an overall scale factor, this cap h of s, right? So if I look at some signal down here and I say that I can represent some signal, right, as some sum of scaled exponentials, right? This is taking this signal x of t and it's representing it using these building block pieces, these exponential pieces, which I know are really easy to deal with in a systems kind of perspective. And this stuff out front, that sum of scaling, right? That sum of scaling that goes on. If I have a linear time invariant system, right? Sums and scales of some signal, like these exponentials, would coming out as sums and scales of that signal small piece, that exponential going through the system. This is going to lay the foundation for what is just going to be a really simple way of taking a look at at a system input-output behavior. So let's go ahead and think about that. So if I went ahead and I took my signal x of t, right, and I ran it into my system, this thing is going to be my linear time invariant continuous system, and I get my output y of t, right? Y of t equals what? It's the system h, right, acting on x of t, something like that. But what is x of t? By this inverse Laplace transform, we know one way of writing this is going to be 1 over 2 pi j, right? Integral c minus j infinity to c plus j infinity, right? And I'm going to have my x of s, something like that, e to the st ds, something along those lines. So in this particular case, I've got the operations of summing and scaling occurring before the system operator, but it's linear time invariant. Linear time invariant says I can commute these operations, right? It doesn't matter which one I do first, summing and scaling, or the system, for example. That's the linearity property. So I can bring that h inside all of that. So if I go ahead and do that, I can write this out as a 1 over 2 pi j, and I'm going to have an integral c minus j infinity, c plus j infinity. H acting on a constant, that's linearity as well. The constant can be pulled outside. X of s is just a constant. And I'm going to have h, right, the system acting on e to the st. And then I'm going to have my ds. I've already looked at, though. I know what my system acting on a complex exponential is, right? I know that is just that same exponential, e to the st times h of s, the Laplace transform of the unit impulse response. And so what I get out of this is 1 over 2 pi j integral c minus j infinity to c plus j infinity. And I'm going to have x of s, right, times h of s. And I have an e to the st ds. I'm going to call this whole thing, it looks a lot like an inverse Laplace transform of something with a, right, with a transform variable, x of s, h of s. Let's just call that guy y of s, right? Something like that. So I have a 1 over 2 pi j integral c minus j infinity to c plus j infinity of y of s, right? E to the st ds, something like that, which I know is just my y of t. That's just the inverse Laplace transform of something with a transform, cap y of s, and it's in the form of an inverse Laplace transform, and we knew before, right, that it was indeed y of t. So what does this tell me? It does tell me what the transform domain representation of the system input-output is, right? I see that y of s is equal to x of s, right, times h of s, something along those lines. This is a transform domain expression, right? Transform. This is a transform domain expression. What was it in the time domain, right? When we looked at the time domain, we had what? Y of t equals x of t convolved with h of t. Both of these things involve, right, finding an output, y, in terms of an input, x, and its impulse response, or equivalently in the transform domain, this thing called the system function, right? So all of these involve y and the mix of x and h, right? In the time domain, you have to convolve those signals x and h. In the transform domain, you just get what? You get simple multiplication. I'm going to make a bet right now that everybody listening to this would rather do simple multiplication than carrying out convolution. This begins to give us a hint, right, as to why we are so interested in this Laplace transform operator. Okay, so let's just try to get into a few kind of nuts and bolts of this guy. I'm just going to make a note here, so I'm going to make a quick note. I'm going to note that Laplace, which I'm going to start kind of indicating through a script L, right? Laplace is what is called a linear. It is a linear operator. We've already talked about linearity as a system operator and what that means. So I could summarize that. I could say that is, for example, that if little x1 of t has a transform cap x1 of s, right? and little x2 of t has a transform. These are all Laplace transforms. We're doing a transformation on there. Cap x2 of s, something like that, right? Then, right, so this is the if part. Then it says that any linear combination of x1 and x2, so ax1 plus bx2, both in the time domain, will have a Laplace transform that is going to be the a cap x1 of s plus b cap x2 of s. This is really easy to prove. You just go ahead and you take this first guy, right? You take this first guy and you plug it into the Laplace EQ, the Laplace equation. What is the Laplace equation? That Laplace equation was that I need to be able to take the integral of that signal, minus infinity to infinity, so put in that signal, ax1 of t, right, plus bx2 of t, and that signal gets multiplied by an e to the minus st, and then we're going to do a dt in there. But what do I know? I know that integration is a linear operator. So those scale factors, a and b, right, can be pulled out. An integral of a sum is the sum of the integrals. All of this stuff allows us to write this whole thing as being what? I could write this as being an a integral minus infinity to infinity of x1 of t e to the minus st, distribute that guy across dt, plus a b integral minus infinity to infinity x2 of t e to the minus st dt, which we recognize as an a cap x1 of s plus b cap x2 of s. And I'm done, right? I've gotten this thing figured out. So a Laplace transform is a linear operator. So that's going to be something that's going to be useful to us as well. I will also say to be useful, Laplace must converge. It must converge for some values of s. Okay, it is commonly it won't converge. That means it won't be finite. It won't converge for other values of s. Okay, and we could say sometimes it may not converge for any s. For any s. And in that case, okay, so in this case, the Laplace transform doesn't even exist. The Laplace transform, right? That Laplace transform doesn't exist. So it is possible to come up with signals that defy being able to be represented in the way Laplace wants to, as this kind of sum of scaled exponentials, because we can't find values of s for which this thing converges. To help get an idea of this convergence, I think I'm just going to demonstrate it by example. So let's do a couple examples. These will be our first examples of taking the Laplace transform of a signal and considering this this convergence issue. When we look at this, when we sit there and they say to be useful, Laplace must converge for some values of s. I'm going to call those values of s. We're going to call this the region of convergence. Okay, and that gets kind of no fun to write out over and over and over again, so we'll just abbreviate that guy as an ROC. Okay, so if we talk about the region of convergence, or the ROC, it's just telling us which values of s does this transform exist for. All right, so I don't know. I get this feeling probably that at this point things are getting a little bit abstract. So let's bring it back down to earth and just do some actual examples. So let's go ahead and take a look at a signal x1 of t being equal to e to the minus at u of t for some real a greater than 0, right? So this is a causal decaying exponential. If I was going to plot this guy out, I could look at this x of t as a function of time, and if I took a look at this guy, it would be something like this. We've seen examples of this. So I've got a causal exponential. I would like to go ahead and take this thing's Laplace transform, convert it from a time domain representation to a frequency domain representation. Right? This x of s basically tells us each of the frequency components that make up that signal. Let's go back and just remind ourselves of that. If we go back to the inverse transform formula, right? What did the inverse transform formula tell us? It said some signal, x of t, right, is equal to a sum of scaled exponentials, right? So it was a decomposition of a signal into a bunch of just everlasting exponentials. They don't have any UTs on there, so e to the STs. And this size for each of the different frequencies being used in that sum, right, are determined by cap x of s, the Laplace transform. The Laplace transform tells us how important or in what amount each of these different frequency components are, right? We have the little pieces that we're using to build up our signal, e to the st. This cap x of s tells us how strong or how much of each one of those pieces, e to the st, are needed to return or find that overall signal, x of t, something along those lines. All right, back to the example. So we're going to have some causal exponential here, decaying exponential, and I would like to find its Laplace transform, find these cap x of s's. We can do this just by definition. So cap x1 of s, right, is equal to an integral minus infinity to infinity of x of t, which in this case is e to the minus at, right, u of t, and then we're multiplying that by that e to the minus st, and then I have a dt in there. The u of t can be absorbed into the limits of integration. So this is an integral 0 to infinity, right? And I'm going to have e to the minus at times e to the minus st. They both have the same base, so I can just add the exponents together. So that's going to be an e, right? And I'm going to have t here times minus a minus s, something like that, dt. This is an integral of an exponential, so we all know how to integrate exponentials. Those are about as easy as they get. So we get back out the same exponential, e to the t minus a minus s, right? And we're going to divide here by minus a minus s. That's just rules of integration there. And we need to do it on the limits 0 to infinity. I'm going to skip at the start here, the first term. So evaluating that mess at infinity, and I'm going to go to the second part, right, which is evaluating at t equaling 0. So e to the 0 times anything is e to the 0. E to the 0 is just 1. So I'm going to have a 1 over, and I can write that minus a minus s as a minus s plus a, something along those lines. So the second term, that arises from the lower limit, right, of integration is going to be a 1 over s plus a. The other one is a little more problematic, right? I get an e to the infinity times something, right, divided by some constant, minus a minus s, something along those lines. The thing I'm trying to figure out is, how do I deal with that e to the infinity? E to the infinity really has a couple of options, right? It can grow without bound, it can blow up, or it can decay down to 0. And we need it to decay down to 0. We need to make sure that this e, right, to the infinity, this is a little bit loose in the mathematical notation, but e to the infinity of minus a minus s, right, over minus a minus s. We need this piece right here. We need this guy, right? We want this. We need this guy, need this to converge. That means go to 0 rather than blowing up. If it blew up, right, we would just get the transform here. We just get cap x1 of s being equal to infinity. That wouldn't be useful at all to us. We need cap x1 of s to be something bounded, something that's converged to some values. We can't have it blow up to infinity. Blowing up to infinity is a non-convergent behavior. So how do we guarantee that, right, e to the infinity minus a minus s, right, tends to 0, right? How do we do that? I'm going to return to the idea that s can be written as sigma plus j omega. I know that s is a complex number, our so-called complex frequency, and I'm going to make that substitution in here so that I can get this e to the infinity, and I'm going to have a minus a, right, minus sigma minus j omega, something like that. And I have a sum of terms for my exponent, so I could write this out as an e to the minus a minus sigma, right, infinity, e, right, to the minus j omega infinity, something along those lines. I'm going to look at the rightmost term first. E to the j something real, right, is just a rotating vector in the complex plane. We had looked at that before. When you have a purely imaginary argument for the exponential, you get a spinning vector. It neither grows nor decays. This doesn't help us converge. This doesn't help, right, converge, right? This guy here just spins. It's just spinning a spinning vector in the plane, and you wouldn't even be able to know what it's spun to at infinity, right? If I take a pointer like on like a twister, if you've ever played Twister, the game, it's got a little dial there that you spin the spinner, right, and it falls on some color, and you go and do your move or whatever. Well, if I flick that so that time went out to infinity, right, where does the dial end? Well, that's really hard to know. It's really hard to know where this spinning vector ends at infinity because that's not really a well-defined point. And even if we could figure out its position, it didn't help us converge to a finite number, right? Or down to that zero value, that convergent value. So this guy out here, this whole piece out here is not going to be something that's going to be useful for us to figure out how to go down to zero to get this whole thing to converge. What do instead we need? We need this first part of the exponential. This is what we need. We need this to go to zero. So let's take a look at that guy. I have e to the minus a minus sigma in this case times infinity, right? And I know that this part up here, just by, let me do that in a different color. We know that this part up here, just because I said a was real, this whole thing is real, right? So I have e to a real number, right, times infinity, and I want it to go to zero. How do I ensure that that happens? Well, that real number better be negative, right? Better be negative. If that thing isn't negative, this thing is not going to converge. So our requirement for convergence, therefore, our requirement, and I think this will become easier as we get along. We don't have to go through the same level of development every single time, right? The requirement for convergence, to make this guy go to zero rather than blowing up to infinity, the requirement for convergence in this case is going to be minus a minus sigma, right? Has to be less than zero. We have to have that thing that leads the infinity to be a negative number. That tells me that sigma needs to be what? Sigma needs to be greater than minus a. And what is sigma? Sigma is just the real part of S. And this is the more traditional way of representing these regions of convergence. So if I can sit there and say that the real part of S is greater than minus a, right? If this is held, right? So if I get that particular condition holds, if the real part of S is greater than minus a, then we get convergence, right? We get that convergence. And what does that convergence mean in our original piece? We were trying to figure out, right, how to take the Laplace transform of my signal. So here's my original signal, e to the minus at ut. We were looking for its Laplace transform x of s. We were going through a bunch of math on that, right? And we were trying to get it to where this thing here, this problematic term, this e to the infinity something, we want that guy to go to zero, right? We want that guy to go to zero. And we just found the conditions for it to go to zero. We need the real part of s to be greater than minus a. So I'm going to get the final bit here. Oh, and it's just taken a little while. So we see what? We see that x1 of s will equal a converged value, 0 plus, right, that minus of a minus. It's just going to be that 1 over s plus a with this idea of the real part of s being greater than minus a. That is my region of convergence, something along those lines. So I'm going to go ahead and box this whole thing. That is my answer in this case. I took the Laplace transform of this causal exponential, and I found that it had a completely different kind of representation. So if you remember what my time domain signal was, right? We had x1 of t, right? That x1 of t in this particular case was equal to, right? It was equal to an e to the minus at u of t, right? Something like that, where we knew that a was real and it was greater than 0, I think is what we did on that, because we wanted a decaying exponential. Yep. So we had that greater than 0 piece in there as well. And that was our time domain expression. So take a look at this guy, right? That's our time domain, t domain expression. And this one up here is our Laplace transform. So this is our Laplace expression. Our Laplace expression, right? It's our transform domain. Transform domain. How do I represent this signal as a function of frequency s instead of time t? The x1 of s, right? You don't see any t's over there. We got rid of the t's through this transformation. So the transform domain provides us a different interpretation or a different way of viewing the same signal. Now through the inverse Laplace transform, I could get right back to x of t if I wanted to, no problem. Let's look a little more at this x1 and see if we can get some idea about this region of convergence and at least part of the reason why it has to be there. So I'm going to go ahead and look at that x1 of s again. So x1 of s, right, is equal to 1 over s plus a. And then we had with a region of convergence of the real part of s being greater than minus a. What I would like to do here is I'd like to look a little bit at this transform. Turns out we got a rational function in this case. S is our frequency variable. Think about a value of s that would cause us a problem in this x1 of s. If I let s be equal to minus a, right? If I did something like let s equaling minus a, what would that tell me? That would tell me x1 of s equaling minus a would be 1 over 0, which would go off to infinity. That's a blow-up kind of behavior, right? That's not convergent. If I am evaluating at values of s that make this thing blow up, right, that definitely is not convergent behavior. It doesn't give me a useful signal in there. We are going to look at things like the values of s that make x of s go to infinity. That has a particular name. We're going to call it the poles of a signal, okay? And so values of s that make some x of s go to infinity are called the poles of x of s, right? And so I'm going to look at that in the complex plane. We're going to call this guy the S plane, right? We had a real positive number, right? We had a real positive number for A. And we said that in this particular case, right, we could not tolerate S equaling minus A, the root of the denominator, something along those lines. So if I had a real positive A, negative A is going to be off on the left-hand plane, something like this. So that guy right there is S equaling minus A, something along those lines. And I've drawn it with an X. We're going to use an X to indicate these pole locations for a signal. And what do we know? This is a part of those frequency values that cannot be included, right? It wouldn't matter what level of oscillation might be paired with that. That would be what value of omega would be paired with that. So anything along that line shares that same envelope, right? That same value. These guys are the stuff that ends up causing this guy to blow up. What did our region of convergence look like? Our region of convergence said we can use any values of s that are greater than minus a. Okay, so if I look at that and I go ahead and shade that in green, right, what do I get? I get all of this s values, any value of s sitting over here, right, to the right of that pole, okay? And this turns out to be a pretty common kind of way of interpreting regions of convergence. Regions of convergence can never include the poles of the signal, right? They never can include the poles of the signal because the poles of the signal, right, are those things that make that signal blow up. So a region of convergence can never include a pole of the signal. It also turns out that if you have a right-sided signal, which I did here, I had a right-sided signal, I had a causal exponential. That causal means right-sided. Right-sided signals will have right-sided regions of convergence. Left-sided signals, we'll find out here shortly, have have left-sided regions of convergence. So this region of convergence tells us the values of S for which we get a convergence in that transform. It can't include the pole for obvious reasons. That pole is what causes that thing to blow up to infinity. And it has this sort of nice memory connection that right-sided signals have right-sided regions of convergence. If you can figure out where the poles of a system are, and you know the sidedness of the system or the signal, you're probably going to be able to make a pretty quick and easy guess as to what its region of convergence is like. Let's just summarize again this one very quickly. So I had x1 of t being equal to e to the minus at u of t, with a being greater than 0 and real, right? Something along those lines. And we found that that guy had a Laplace transform of x1 of s, right, being equal to 1 over s plus a, right, with a region of convergence, real part of s, being greater than minus a. I will say that when you're doing bilateral Laplace transforms, it is absolutely crucial that you include that region of convergence. Your answer is not complete without that region of convergence specified. Let's go and do another example that I think will help highlight why it's so absolutely necessary to do that. So as another example, so this is going to be my second example, something along those lines. Let's go ahead and look at some signal x2 of t, and I'm going to let that guy be equal to minus e to the minus at u of minus t with, right, a that is real and that is greater than 0, something along those lines, okay? And I would like to go ahead and carry out its Laplace transform. So I'm going to find x2 of s, and by definition, I know that's an integral minus infinity to infinity of the signal, and the signal in this case is minus e to the minus at u of minus t, and then I have an e to the minus st, and I'm just doing a dt on that. The u of minus t is going to give my limits of integration here going from minus infinity to 0, right? I can pull that minus sign up front if I want, and I'm going to have again an e, right? And I'm going to have at minus a minus s, and I'm going to have dt. So this thing looks very, very similar in many respects to what we just did. Not a big surprise, it had a very similar form. It was still an e to the minus at type of thing. So if I go ahead and do this, I'm going to get a minus, and I'm going to have what? I'm going to have e to the t minus a minus s over minus a minus s, right? Evaluated in the limits minus infinity to 0, something like that. Use the upper limit one here. I'm going to have e to the 0. E to the 0 is just 1. So I'm going to have 1 over minus a minus s, but there was a minus sign out front. That's going to give me a 1 over s plus a, right? And then I'm going to subtract off of this. So I'm going to do a subtraction, right? And it's going to be a subtraction of another negative of another negative. So it's just going to be a single negative up here. And I'm going to have an e to the minus infinity, if you will, minus a minus s, right, over s plus a. I did some combination of some minus signs in there. This guy here, we need to go to 0. We need this to converge, right? That e to the infinity part is problematic. So how do I ensure that that happens? Again, it's all dependent on this term up here. So if I take a look at that guy, I'm going to have an e to the minus infinity, and let's go ahead and write that as a minus a and put s in terms of its rectangular form. So minus sigma minus j omega, something like that. This whole thing would be like an e, right? And I would have an a plus sigma infinity, and I'd have an e to the j omega infinity. This first part here, right? This part that is the e to the j something real, that just spins, right? We know that that's just a spinning exponential. So this guy spins, it spins, right? Doesn't help us get to 0. This one, we need to go to 0. So how do I ensure that e to the something times infinity goes to the 0? Well, I need a plus sigma to be less than 0, right? And that, if I solve for it, is sigma less than minus a. That is my region of convergence. If that is true, right, this guy, this term up here, will go to 0. So this thing goes to 0 if, right, sigma is less than minus a, the region of convergence. That's how I get convergence, and I am just left with then, right, this term up here. So I can put all that together and I can get my final result. I get x2 of s, right, as being equal to, I'm going to have a 1 over s plus a, right, with a region of convergence of the real part of s, which is just sigma, right, being less than minus a. Okay, that would be my final answer in there. Okay, I went ahead and did the math, and I got an expression for some values of s that let it not blow up to infinity, that region of convergence. Remember where this came from, right? This x2 came from a little x2t being equal to what? It was that minus, right? It was a minus e to the minus at u of minus t, where a was real and positive. So it was a minus e to the minus at u of minus t with a greater than 0. If you plotted that kind of signal out, the minus sign out front, right, just means it's a negative signal. E to the minus at, if a is positive, that whole thing out front of the t is going to be a negative number. And as t heads off to minus infinity, it grows. U of minus t tells us it's only negative times that this thing is non-zero. Anything to the right of that is 0. So we have, because of the u of minus t, it goes like that. And then because of the minus sign out front, I'm going to have a negative signal. And because it's e to the minus something real and positive times t, as t goes to minus infinity, I get e to the plus infinity. So that guy's going to grow. It's an anti-causal growing exponential, right? Go back to what our x1 was. Our x1 of s was equal to 1 over s plus a, with a region of convergence, real part of s, right, greater than minus a, right? And what did that guy correspond to? It was an x1 of t equaling e to the minus at ut, again with some a greater than 0. And if I plotted that one in there, what did we get? We got a completely different looking signal, right? It was a causal signal, and it was a decaying exponential. So let's finish this lecture out by just noting a couple things. I'm looking at two different time domain signals. The first signal that we looked at, right, this x1 equaling e to the minus atut, was this nice causal decaying exponential. We found its transform. X1 of s is 1 over s plus a. And then we specified the values of s for which that transform converged, real part of s greater than minus a. And we noted that that expression, right, pointed us on the right-hand side of where the pole of that transform was. So if I came in here and I found the pole, that pole is at minus a, right? You can't include that guy in the region of convergence. And so we came over here and we said, hey, the region of convergence is everything over here to the right, something along those lines. Our second signal that we did was x2 of t minus e to the minus at u with minus t, which was an anti-causal growing exponential, right? Take a look at those two signals in there. Take a look at those two signals between these two cases. Those are not equal in any form or sense, right? They are about as different can be. One's causal, the other's anti-causal. One's a decaying exponential, one's a growing exponential, right? But if I look at the transform, just the part that doesn't include the region of convergence, x2 of s is 1 over s plus a. x1 of s was 1 over s plus a. These guys happen to have the same transform. The only thing that was different was the region of convergence. And in this case, we had a left-sided signal, and it turned out, like I had said before, it just turns out this way mathematically that regions of convergence match the sidedness of the signal. So we still had a pole, right? There's still a pole because they have the same transform of 1 over s plus a. They both have a pole at minus a, right? Something along those lines. You can't include that guy in your region of convergence because that's what causes it to go to infinity. In this second case, right, its region of convergence was instead off to the left. So what we see here is that if I just specified that rational function part, it would not be enough because these two very different looking signals, right, have the same kind of rational expression, the same cap x of s, right? The only thing that is different in there are these regions of convergence. If I did not specify the region of convergence, I would not have known which of the two signals I had originated from. Okay, very, very quick recap then of what we've done. We introduced this idea of moving away from the time domain to the transform domain. We're going to do that through something called the Laplace Transform. We motivated that by looking at what happens when you take a complex exponential, e to the st, into a system. And what we found is we got e to the st times a complex constant, h of s. And we recognize that h of s from our circuits class as just being the Laplace transform of the unit impulse response. So cap h of s is equal to the Laplace transform of little ht. We introduced what was also the inverse Laplace transform, mathematically difficult for us to do, but helpful conceptually. That inverse Laplace transform tells us what? Any old signal can be represented as a linear combination of complex exponentials. And our understanding that complex exponentials go through a system so simply is a great motivator then why this Laplace transform decomposition, this way of representing signals, is so advantageous. We looked at the fact that the Laplace transform was a linear operator, and then we decided to go ahead and do a couple of examples of carrying out this bilateral Laplace transform by the definition and just seeing what this new representation of the signal was. It's completely equivalent in information. It's just a different perspective of the signal where we're replacing the time variable t with a frequency variable s. We're going from a lowercase signal, little x of a time variable, to a transform domain, so cap x of the frequency variable s. We said that for this transform to make sense, for it to be useful for us, it has to be able to be a converged value. It has to converge. It can't blow up to infinity. And we took our two examples and we found that there were definitely values of s that cause that expression to blow up to infinity. We ended up getting a kind of an empirical view that number one, regions of convergence can't include poles of our transform. And number two, the region of convergence matches the sidedness of the signal. So if I had a right-sided signal, we're going to see a region of convergence to the right of the pole. If I had a left-sided signal, we're going to see a region of convergence that's to the left side of the pole. Next time, we're going to go ahead and continue our discussion of Laplace transforms, also talk a little bit about inverse Laplace transforms, and then cover a bunch of properties as well, which will help our ability to take Laplace transforms both efficiently and have some intuition about both signals and systems. That'll be next time.